Now let's venture into an exploration of vessels. The blood vessels are the arteries, arterioles, capillaries, venules, and veins. They form a closed tube that carries blood away from the heart to the cells and back again. The arteries and arterioles are vessels carrying blood away from the heart. In the pulmonary system, these will be carrying deoxygenated blood. However, in the systemic circuit, they will be carrying oxygenated blood. The arteries are the strongest, most elastic vessels, and they're adapted for carrying high-pressure blood. Arteries become smaller as they divide and give rise to arterioles. So arterioles are basically smaller arteries. The wall of an artery consists of endothelium, tunica media, and tunica externa. You can see that all three layers are present in both arteries and veins. However, in the artery, we have a much thicker tunica media or smooth muscle layer, because the arteries actually have some contraction strength themselves as they vasodilate and vasoconstrict in order to maintain vascular tone. The arteries are capable of vasoconstriction, which is when they become smaller, and vasodilation, which is when they become larger. These vasoconstriction and vasodilation actions are controlled by sympathetic impulses. So when the sympathetic system stimulates, the vessels will constrict. And when it's not there, the vessels will relax and become more dilated. Once we've gone through a series of arterioles, the blood will finally reach the capillaries, which are the smallest vessels. They consist of only a layer of endothelium, through which the substances will be exchanged with tissue cells. Some of the substances pass through slits, some of them pass directly through the endothelial cells, and some of them pass between. Capillary permeability varies greatly from one tissue to the next. Generally, more permeability will be found in the liver, the intestines, and certain glands. There'll be less capillary permeability in the muscle and considerably less in the brain because of the blood-brain barrier preventing movement of substances out of the vessels. Shortly, we'll look at the sorts of substances that are passed through the capillary walls. The pattern of capillary density also varies from one body part to the next. In this figure, you can see how an arteriole delivers blood, and it branches off into many capillaries. Nutrients are passed out through the capillary walls into the tissues, and wastes are picked up here and then returned into the venous system. Areas with a high amount of metabolic activity, like leg muscles, for example, have a much higher density of capillaries because they need much more oxygen delivery to do their function. But of course, the muscles of the leg are not always in action. If we're sitting on the couch watching television, we don't need a lot of blood supply into the leg muscles, but we may need a lot of blood supply to our digestive tissues as we digest our meal. This diversion of circulation is controlled by precapillary sphincters. That is, at the edge of the arterioles, before they branch into capillaries, there are little sphincters, muscular closures, that can close off the vessel and prevent blood flow into that area. These capillary sphincters are controlled by the oxygen concentration in the area. So when oxygen concentration in this region is low, the sphincters will open and allow blood flow into the capillaries. However, when it's high, those sphincters will close and shut off blood supply to that area. The blood is needed elsewhere in the body. Let's say we're in the rest and digest phase. Why have all that blood sitting in our leg muscles when we could easily divert it to the digestive system to take care of all of our digestive needs? So, a little more information on how exchanges happen in the capillaries. The blood entering the capillaries contains high concentration of oxygen and nutrients that we need to get into the tissues through the capillary wall. So here we have a capillary. And here we have some tissues. There are small spaces, as you can see, in the endothelial cells of the capillary. Hydrostatic pressure will drive fluids out of the vessels and into the tissues. Now, these spaces that things can pass through are relatively small, so all the large proteins and blood cells will stay in the vessels. So at the arterial end, we have a large hydrostatic pressure pushing from the vessels into the tissue. Now the tissues also have fluid in them, so they have a force that pushes back. The osmotic pressure from the tissues pushing back, though, is much smaller than the hydrostatic pressure pushing in. So even though there may be an exchange of fluids, the net outward pressure causes nutrients to be delivered to the tissues. On the capillary side, we've now got more fluid and nutrient in the tissues, so the outward force is less and the inward force is more. So the outward force of the hydrostatic pressure is still pushing a little bit of nutrient and oxygen and such into the tissues. However, the tissues are very rich now in waste products and carbon dioxide. That force from the tissues will push these wastes back into the capillary on the venous side. So this case, the inward force of osmotic pressure outweighs the outward force of hydrostatic pressure, and so we have net inward movement of fluids, waste products, carbon dioxide, and such, so that it will flow back into the venule. Most of the tissue fluid will return in the venous supply back towards the heart. However, some of it will remain to go through the lymphatic vessels. So lymphatic vessels collect all the excess fluid and return it to the circulatory system. But on the way, it's going to check for invaders. We'll explore the role of lymphatic vessels further when we go into the immune chapter. Blood then returns through the venules and veins. Now, as we explored earlier, the venules and veins have a little bit different structure. Although they still have the 3 layers, they have a thinner muscular layer, so they can't really act to pump blood back. You'll notice this difference when you take a pulse, say on your arm or in your neck. You can feel the pulsation of the arteries. However, the veins, we don't see that same pulsation. That's because they have a thinner muscular layer. The venules are the first stage leading from the capillaries back towards the veins, so they're essentially small veins. Once blood makes it back into the veins, they'll run into some flap-like valves. These flap-like valves prevent backflow so that we can move blood against gravity back towards the heart. Now, this is quite a challenge with so much less muscle in the wall of the veins. How do we possibly get blood back to the heart? We'll explore some of these mechanisms coming up shortly. The blood pressure and all the components that maintain it is key to this return. Blood pressure is the force of blood against the inner walls of the blood vessels, anywhere in the cardiovascular system, although the term blood pressure is usually used to refer to arterial pressure. The arterial blood pressure rises and falls following a pattern that's established by the cardiac cycle. During ventricular contraction, arterial pressure is at its highest. This is what we call systolic pressure. When the ventricles are relaxing, the arterial pressure is at its lowest. We call this diastolic pressure. Different than the systolic phases and diastolic phases of the atria and ventricles. However, it corresponds to ventricle systole and ventricle diastole. With each heart pump of the ventricles, the surge of blood that occurs can be felt in certain points throughout the body. This is called pulse. As the blood exits the heart and goes into the aorta, The aorta is actually fairly elastic and expands to allow that. That expansion causes contraction of the muscle in the artery, and that artery contracts against the blood itself. And so the arteries actually have a slight pumping action that aids that of the heart in circulating the blood. Now, naturally, the further through the arterial system that we get, the lower the pressure will be. Very close to the heart, we see a big difference between the pressure seen in systole and that seen in diastole. The normal range for blood pressure would be 120/80, that is 120 millimeters of mercury during systole, and 80 millimeters of mercury during diastole. As we get further from the heart, the difference between systolic and diastolic pressure declines. And when we get into the capillaries, there is really no difference. We can't measure a pulse in the capillaries after all. As we return into the veins, the system becomes lower and lower pressure. So how do we get the blood back to the heart when there's really no pumping action? There are many things that influence arterial blood pressure. It depends on the heart's action, the blood volume that's being pumped, the resistance that the vessels have to the flow of blood through them. That is, are they elastic or are they very tight? And then the viscosity of the blood. How thick is the blood? The heart action is dependent on the stroke volume and the heart rate, which together are called cardiac output. If the cardiac output increases, that means there's more blood going into the vessels, and thus it will put more pressure on the vessels. So we experience higher blood pressure with higher cardiac output. Something that's really interesting is the action of the vessels. As I've said, they're fairly elastic, and thus they expand as a large pressure is put in there. That acts to dampen the possibilities of pressure. People with atherosclerosis, however, have hardened arteries, so they're not nearly as elastic. And so we see a much bigger difference in the systolic pressure because the vessels are unable to absorb some of that pressure. Now, blood volume definitely will affect arterial blood pressure. Blood pressure is normally directly proportional to the volume of blood within the cardiovascular system. As the blood volume increases, then so will blood pressure. If the blood volume decreases, then blood pressure will also decrease. Blood volume will vary with age, body size, and gender. Peripheral resistance is another aspect that will influence blood pressure. Peripheral resistance is about the friction that we see between the blood and the walls of the blood vessels. As the peripheral resistance increases, like when the vessels are constricted, the blood pressure increases. A way to think about this is that a river will flow in a larger space at a much lower rate than it will if we take that same volume and push it through a smaller canal. It'll flow much more quickly. We also see that it'll flow more quickly down the center because in the center there isn't resistance from the edges of the canal. Same thing happens in the circulatory system. In larger vessels, blood will flow more quickly down the center than it will along the edges. So the smaller the vessels, the more the resistance, not only because they're smaller spaces, but because there's more surface area to provide friction. Another factor that will affect blood pressure is the blood's viscosity. Viscosity is essentially thickness or how easily it flows. You could imagine syrup versus water. Syrup flows much more slowly than the water would. The greater the resistance to flowing, the greater the blood pressure. Blood viscosity is affected by a number of different things. It can be affected by how many red blood cells there are. If there's too many red blood cells and not enough hydration, then we'll see increased viscosity. Hydration is really key to keeping the blood's viscosity appropriate. Blood pressure is controlled in a number of different ways. It's determined by cardiac output and peripheral resistance, as we've explored. The body maintains normal blood pressure by adjusting the cardiac output and the peripheral resistance, so we can add a larger volume being pumped from the ventricles at a faster rate to increase the cardiac output, or we can vasodilate and vasoconstrict the vessels in order to increase or decrease peripheral resistance. The balance here is integral to maintaining homeostasis. The cardiac output, again, depends on stroke volume and heart rate, and a number of factors can affect the cardiac output. If the arterial pressure increases, the cardiac center and the medulla oblongata sends parasympathetic impulses to slow the heart rate. If the arterial pressure drops, the medulla will send sympathetic impulses to increase heart rate to adjust the blood pressure. Other factors such as emotional upset, exercise, and rise in body temperature can result in increased cardiac output and thus increased blood pressure. So another example of why it's so important to manage stress. Emotional upset can really put us into a state of increased blood pressure. And it doesn't have anywhere to go because we're not exercising. So managing our level of stress not only will keep those levels of cortisol low, but also help us keep our cardiovascular system healthy. Now, there's a vasomotor center in the medulla oblongata, and it can adjust the sympathetic impulses to the smooth muscles in the arterial walls and adjust the blood pressure. Certain chemicals, such as carbon dioxide, oxygen, and hydrogen ions, will be detected at centers within the circulatory system, and this can also have an impact on the peripheral resistance, how vasoconstricted or vasodilated the vessels are. So, as we've explored, blood pressure decreases as it moves through the arterial system and into the capillary networks, so that very little pressure remains at the venous side. Blood through the venous system is only partially the result of heart action, and instead also depends on a number of different factors. Here is how we're going to return blood to the heart through this very low pressure venous system. Skeletal muscle contraction around the veins acts to push blood past the valves so that it can return to the heart. You'll notice this when you're in an airplane or if you sit still for a long time. You'll get venous pooling, that is, the blood in the venous system without the action of your muscles has a really hard time returning against gravity towards the heart. Another thing that helps this is the movement of breathing. It changes the pressure in the thoracic cavity. So when we inhale, it adds greater pressure, but when we exhale, blood is pushed up through the thoracic cavity. So this pumping action also helps return blood to the heart. We'll also see vasoconstriction in the veins. That is, they become smaller. Although they don't have a lot of muscle, they do have some, and so they can tighten up around the blood and aid in its transport back to the heart. So take a moment here to write down as much as you can remember about the regulation of blood pressure. Think about cardiac output. What factors influence cardiac output? Also consider the figure in your text that shows how substances move out of the capillaries on the arterial end and how they move back on the venous end. This will probably be part of your diagramming assignment for this week, so really firm up that in your head before you move on.